this challenge. So every leaders or someone take the notes with his next report. And we start for the preparations for the reporter, 5 minutes. 技术升级了。Okay, so sorry about the technical problems. So our stage will be taken by the reporter. You have 12 minutes. Okay, start.
Honorable judges and fellow competitors, I'm the reporter from Team Definition, and I'll be reporting problem number 11, balls on elastic band. So first we'll read my outline. I'll first start with the introduction, talking about the problem statement, our focus, and the setup. Next, we'll move on to the theoretical model of our own theory, which will talk about the differential equations and about the energy. And for the experiment, we'll be mainly talking about the systems analysis and the periodic motion. And last, for the further discussion, we will talk about the non-ideal condition and where the error can come from. So for the problem statement, connect two metal balls with an elastic band. Then twist the elastic band and put the ball on the table. The balls will begin to spin in one direction, then in the other. Explain this phenomenon and investigate how the behavior of such a pendulum depends on relevant parameters. So we believe our focus will be mainly on 2 points. First is its periodic motion and how energy leaves the system. So this is the motion of one of the balls. As you can see, it's doing like a spiral going outwards, and later on we're going inwards. So first we'll model for a simplified view. This is the side view from the two balls and the elastic band in the middle. The original length of the elastic band we call it L, and the length that it lengthens on the one side of the rubber band we call it R. And from the radial view, we define theta as the twisting angles. So for our theory introduction, let's first talk about our approximation of the real condition. So by writing down the equations of motion through the linear axis, we can get two equations. First is the rotational one, and then is the linear one. On the rotational one, we assume that there will be a damping force, damping torque created by the rubber band itself, so we write it like V. And then on the tangential side, we believe that the ball is having a pure rolling motion, so there should be a rolling resistance that's going to be negative work on it. And there's also a twisting constant. On the linear side, for one single ball, we believe that there will also be damping on the radial side through the material of the rubber band, and there will be sliding friction on the radial side where the ball is going outwards and inwards. And at last, we implemented this pointing effect into our consideration. Pointing effect talks about how a solid, when you twist a solid, it actually lengthens it. So when there's twisting, you actually lengthen it more. And we think that the sliding friction shouldn't affect the rotational motion, but still takes away energy from the system, and mainly on the elastic potential energy. The reason for that is because the direction of the force is on the radial axis, and the spinning, the direction of the spring is also on the radial axis, which means that its speed, its velocity is on the tangential side. So these two shouldn't affect each other. But however, those two equations don't have a simple solution. So we will consider a more ideal condition, which first we suppose the two rolling elastic bands have mirror movements. We regard the system as two metal balls, and the axis that runs through the middle of the two balls adds up to the rotational inertia, which we calculated over here because we're using a solid metal ball. So the moment of inertia of one of the balls should be 2/5 times mr squared. And we suppose that it's a pure rolling motion, so we first neglect the rolling resistance for approximation, and then we assume the source of energy loss is the effect of total damping. So we can write down the differential equation as follows. And to further talk about this differential equation, this actually has a similar solution, which we can write down. And if we put it to the initial condition, which is theta 0, we can get its amplitude, its angular frequency, and the initial angle. And by further investigating in this equation, we can get its energy loss throughout the system, which we can write down as follows. And we can approximate it into the blue dotted line. So for our experiment setup, we use a tripod and a high-speed camera to record the balls on the speaker spinning from the above. And then we use different surface materials like the screen pad and table. They all have different friction to analyze each other. And first, we'll talk about the torsion constant and the damping coefficient we previously mentioned. So to measure it, we first use tracker. We use a simpler pendulum like this, and we spin it with a slight angle, and we film it from above so that we can use tracker to try it on the green dot to see whether its kappa and its PD value is. Because it's an elastic band, so it's actually also a damping motion. Although we can approximate this into a normal harmonic motion, but it's still damped, which is the damp constant is what we consider inside of our first approximation. So using tracker, we can get the angular velocity actually decreases with the amplitude. So we can write down, we can approximate that into an exponential form, and then get the value of B. And next, we'll talk about the rolling resistance. We first approximate that the coefficient of rolling resistance is approximately 0.004. And from now on, when we're talking about the rolling, we'll first be focusing on the half of the period, which is when the ball expands and goes into the largest form and contracts again. But however, the real period should be when it springs back, since that's when the theta actually goes back to its original state. So we only first talk about the first these triangular feet. So in that, we can calculate the turns of distance that the ball traveled and calculate it into the work that it's done. And next, we're talking about the damping from the whole system. So we're following the theory, we're assuming that radial sliding friction only affects the elastic potential energy, which the only damping effect period is tangential. So we derive from the original formula, we can approximate this value into a damped one. And then by using the energy equation we previously mentioned, which is the one that we assume the only energy loss is from the damping, we can get the only work that dawns on it, since it's tangential, should be this rolling resistance. So we write it down as follows, and we can get the average B value. And we can find that the actual B value is actually greater than the rolling the B value inside of a rubber band. So we can conclude that the rolling resistance cannot be ignored, and its effect on the rubber band, the balls, is greater than the damping inside of the rubber band. However, when we're trying to fit the original equation we mentioned, we can actually see that there is energy gap between the peak and the theoretical line. However, when we're calculating the theoretical period, it actually still matches with the actual scientific data pretty well. So we assume that the energy loss could be from the radial sliding. So to consider the radial sliding, the main force that is running on it, you assume that it should be the sliding friction. To calculate the force, the work that's being done by the sliding friction, we first use we approximate the coefficient of sliding friction, and then we can use tracker to calculate to track how much when the elastic band lengthens and contracts. And add up the distance, we can calculate the total, we can approximate the total work that's been done by the sliding friction. And interesting enough, the work done by the sliding friction is actually greater than the rolling resistance, which caused the energy gap we previously mentioned. And next, we're going to talk about the initial condition, which is the other parameters. We found out that there's no significant effect on the periodic cycle, which we use the 100 turns and the 160 turns. We only calculated the first cycle because we wanted to ignore most of the other errors. But however, there is still quite a significant error, which is called when we calculated it. And we will explain it what the possible factor could be later. And the other experiment we do is for different friction. We say previously we use a 160 turns and we use it on a rougher surface. We can actually get that the period becomes bigger, which is our theory that when the coefficient of rolling resistance increase, the time period should increase as well. But another thing that we can observe is actually that there is less total cycles, which we think that it might also be because of the sliding friction created by the balls, because it's bigger, so it takes a lot more energy away from the system. And for the further discussion about the error that I previously mentioned, we think that it could be coming from a few parts. So the first will be the unevenness of the surface. Since the surface cannot be perfectly even and the ball cannot be perfectly smooth, there could actually be bouncing, just like this below. The ball bounces up and there's collision happening with the ball and the table, which takes away more energy. And the other one is the bulking that happens between the rubber band. They actually ball together. There will be a few things that could happen. First is the energy is constrained inside of the rubber band, and the other thing is that when it touches the ground, it actually increases the friction. And another factor is about temperature. Temperature actually affects the coefficient of kappa a lot, but however, we always do the experiment inside of the same room at good room temperature, so we don't think that would be really significant. So for a conclusion, we know that the initial angular position does not affect the period of such a pendulum, and friction, specifically rotational friction, is negatively associated with the period. And the period is mainly affected by the rotational inertia, the kappa value, and the average damping coefficient. And the damping effect caused by the friction is way more influential than that caused by the torsion. The radial friction only affects the elastic potential energy stored in the elastic band, thus the energy taken away will not affect the period. And as Eric can be explained by ball bouncing up the uneven surface and rubber band touching the ground creating friction. And that's the end of my presentation. Thank you.
Is there a limitation of spinning motion of the pendulum caused by the initial potential energy?
Oh, you mean the limits?
Yes. Well,
you mean
will there be a
there's
limit to
no
when it will spin?
Oh, yeah, there should be, because
So that will be.
yes.
Okay. Is the moment of inertia a time-dependent variable?
We don't think that's a time.
Okay. Should the elastic band's elevation be considered?
I think it should be considered.
Okay, thank you. Is the whole system proving or it will slide?
I'm sorry, it's green.
Is the system considered by the proving or it will slide?
It will slide on the radio axis.
Okay, thank you. Which kind of friction is acting on the ball?
We think that will be sliding friction and then the connected friction and the rolling resistance.
Okay, thank you. Will the twisting direction of the elastic band affect the rotational behavior?
We don't think. Oh, yes, will affect how it spins the direction.
Okay, thank you. Will the elastic band generate elastic fatigue during the oscillation?
Yes.
Okay, thank you. Are the angular velocity of each side of the ball the same?
We believe so.
Okay. At the end of the motion, will the pendulum stop at the balance angle or the balance length?
You mean?
It will stop.
Yes, it will.
It will balance in the balance length, right?
Yes.
Okay, thank you. What's the most important factor affecting the motion?
We believe that it's actually the rolling resistance.
Please send to your observation field. Yes. Can you know when will it transform into sliding instead of pro-moving?
Oh, I think there's only pure rolling on.
Did you do experiment to prove it?
No, we didn't.
No. Okay, thank you. boundaries and competitors. I'm from Team Excelsior. Today what I'm going to oppose is problem number 11, balls on an elastic band. Here's a problem statement. Connect two bending balls with an elastic band, then twist the elastic band and put the balls on the table. The balls will start to begin to spin in one direction and in the other. Explain the phenomenon and investigate how the behavior of such a pendulum depends on the relevant parameters. And my main focus is how the potential energy causes the balls to rotate, and analyze the pendulum behavior and how the relevant parameters affect the behavior of such pendulum. This is my structure of solving a problem. First, I would like to discuss about how the energy will transform cause the system to rotate. Will the elastic potential affect the motion, and will the connection energy cause it to rotate? And will there be coupling constant and about the damping? And then I will analyze the pendulum behavior of the system. Will the periodic of the motion be the same by each when you change the parameter? And will the elastic band indication cause the difference of the behavior? And how does the relevant parameter influence the pendulum behavior, such like the initial turns and the twisting angle? And will the mass of the ball affect the pendulum behavior? And the elastic coupling constant, will it need to be considered? And here's the reporter's pros and cons. First, the reporter did good on the observation video of two balls rotating and tried to use theory to describe the pendulum behavior, but failed to clarify kinetic energy distribution of the two balls. Did not mention the boundary condition may cause to rotate, and lack of measure of rotational coefficient. But he did good on the clear explanation of the main cause of the energy loss. But he did not consider rolling and sliding situation, such as when will it change between the rolling and kinetic friction. And he did well explain on the energy transformation, but he did lack of parameters. And I also think the mass of the ball and the spring constant would affect the motion, and not well explain the parameter affect the pendulum behavior. Here's the points to be discussed. First, I would like to discuss about the energy transformation. How do you store your potential energy, and will there be energy loss? And for the kinetic energy, how it causes the acceleration, and will it be affected by the movement of inertia? And by the contact friction, what is the rolling motion of it, rolling or sliding? And the pendulum behavior, the periodic motion, will there be the same period of the ball in the system? And how the elastic and torsion coupling constant affect the motion? And the mass of the ball and the elastic band, I think I want to discuss about how it affects the pendulum behavior. And the elastic elongation, it will also affect the pendulum behavior. And such as the elastic and coupling constant will affect the elastic band elongation. And I want to discuss about the shape while twist. And the parameter, this is the rotational motion. I want to know about how the friction coefficient is calculated, and how initial turns will affect the phenomenon, and will it have the boundary condition to let it rotate. And the elastic constant, how will it affect the motion and mass of the ball. And I want to know about when the elastic band is shorter than the original length of it. Will it still generate a kinetic energy inside it? And the damping, which is the contact friction, will cause the system to act like this. Please turn to your instrument 3 where the damping. You have mentioned that the motion there will be sliding of the motion. Can you explain it why?
Oh, you mean this one?
Yes. Why will there be sliding?
Oh, we believe the sliding is from when the ball goes outwards and inwards.
Yes.
Okay, why would there be?
Why will there be sliding motion?
Why would there be sliding motion in this direction?
Yes. When the ball rotates, why will it slides?
Because it has to elongate with the rubber band.
So you mean the sliding is caused by the elevation of the elastic band?
Yes, and also the centripetal force applied with.
Will the ball slide on
the tangential side?
Yes. Yes.
We don't usually consider that.
You think your okay? So the problem. Please turn to your observation video. The ball starts to rotate, right?
Yes.
And when you store the initial energy of it and releasing it, what will happen to the motion?
We believe that twisting actually makes the ball to rotate, and when it starts rolling, it gains the velocity.
Yes, and why will it stop and rotate in another direction?
Why would it stop and rotate in the direction? Okay, because when it's at its when the spinning of the theta is approaches zero, it actually has its maximum speed, so it keeps rotating back.
So it won't stop. It won't stop, right? Because you said that this is rolling and it said it is not sliding, so
Yes.
it will not stop.
Oh, that's a good point. Okay, we can investigate that more in the future.
Like you said it has damping motion, right?
Yes.
So the opponent thinks that if there is damping, is caused by the sliding of the ball. So the system will finally stop rotating.
Okay, I believe maybe when the ball is actually at its at the stage of like almost done with its rotation, it might turn into
Okay,
sliding.
thank you. You have mentioned the short question. The moment of inertia is not a time dependent value, and why?
Because when we're doing with the equation, we go back to the page.
Can I use the backboard?
Sure.
Will you complete? You have mentioned that the rubber band will stretch, right?
Yes.
So can you write down the moment of inertia of the system?
We're looking at through the radial axis. So the moment of inertia is described by around this axis should be.
Well, the radius of the system, the radius of the rotating system causes the moment of inertia to change.
I don't think so.
You don't think so? So when the force is like this, right?
Yes.
It's the original then
Yeah.
yellow.
Okay.
And when it is up, and when it's stretched, it becomes to this.
Yes.
We'll call it air prime. So will this moment of inertia be the same?
From my equations, I don't think so, because we're only talking about the radial axis. And if we don't consider the mass of, okay, maybe this should be considered, but
Okay.
as that's the
Okay, I got it. Because the opponent thinks that there consists of mass, and you change the radius of the rotating system, it will affect the moment inertia. Okay, thank you. What do you think that increasing the spring constant will affect the motion?
If you see the spring constant,
Yes.
I don't really think it would affect. Oh, but if you increase the spring constant, I believe the gamma value will also change.
No. So
The torsion constant will
Yes,
also change.
and,
I believe so. They are
the elastic constant, the
the gamma. Oh,
no, the kappa is how do you define the kappa?
Oh, the torque is
The torque is kappa.
this.
Okay,
So
so
do you mean by
so for the L innovation which is
this one?
this one.
Okay.
When you increase the K right here, what will happen to the motion?
From my belief, because all of these constants are related to the material, so if this change, this might change too.
Okay,
So
so
I believe it's only related to this, not the K.
what do you think when the rubber band length will never change? What will it affect to the motion?
If the ribbon
Yeah,
never change?
will never change is then.
I believe it was just, no, it has to change. Because you're twisting it, there's no such
I
thing
think
as a complete
this-
rigid body.
Rich body. So
So
if you increase this number, it is hard to integration, right?
Yeah.
So when that number is very big, it can be seen as it will not belong, right? Or it will belong very small.
I don't think so, because when we're talking about this, it's always related to the material. So
Okay,
it's
got it.
also related to this.
The opponent thinks that as I mentioned before, the moment inertia will be depends on the radius of the system. So
Sorry,
when
I don't think that's the case.
the moment of inertia can be right like this. Which the R is the time depending is the time depending variable, which when as you mentioned in your report, the elastic band will stretch, right?
Yes.
So it will be longer.
So
when it be longer-
clarify something?
Yes.
I believe the potential inertia you're writing is actually when we're seeing this on the above, when we're see this as the
rotational axis,
and the
right?
rotational.
Yes.
But what I'm talking about is not that. We're actually talking about when we're looking at the radial axis and it spins like this.
Okay, so when you see the system rotating like this,
Yes.
when this
So, yes,
this
the
system
moment
will change. So when what do you think if you increase this will affect the motion? You said it will increase the moment inertia, right?
Yes.
Then what will affect it to the system?
You mean when if I could change moment inertia, can I change the mass or it's only
No, the K.
okay? I believe that.
Will it spin faster?
Do
you agree?
Yes.
Okay, so the opponent thinks that because when the elastic band is longer, it increase the moment inertia, which let the period of the motion be longer, so it will affect the motion like this. Okay, when you consider this is ball and this is another ball, but
They're different.
yes, but they are different. The mass of the ball are different. What will happen to the motion?
I believe the center of mass will actually start to rotate.
You mean the center of the mass will start to rotate?
Yes.
So the center of mass, what is the axis that is rotating from?
You mean the axis? Well.
You agree that the ball will spin on the axis of the center of the mass. We also that the center of the mass is here.
I don't think so.
Okay, the opponent disagree to your opinion. Thinking that the trajectory of the bigger mass will be like this, and for the bigger will be like this.
The reason why I think about this is because the sliding friction on the radial axis is actually proportional to its own weight, the normal force.
Okay,
So there's
okay,
simply a difference. Or maybe there's a misunderstanding, but that's from my
Okay, thank you again. And if you consider the mass of the ball is same, but the radius of the ball isn't the same, what will it happen to the motion?
well, the radius changed. So in a non-ideal condition, the motion flex surface will be going on like this. Right?
Yes, so what will it affect to the motion?
I believe that because since the rotational axis is actually different.
The draw, where will it rotate?
Where would it rotate?
Where is the rotational axis? In another way, where is the center of the mass?
The center of the mass. The center of the mass should still stay at the middle position.
Okay, and where is the rotating axis?
The rotating axis, I think it will be slightly over to here.
The opponent disagrees to what you think. The rotating axis will be like here. This is the rotating axis.
Okay.
So this is rotating axis. So when the radius of the ball is different, it will result like this. It will start to rotate this way. Do you agree?
Yeah, that seems.
Okay.
But however, I want to ask the point about this because since the rotation axis, you agree that it's with on this axis since it's twisting vectors on that.
Can I move on to the other things? Okay. You have mentioned that it has rolling and friction, rolling friction and sliding friction, right?
Yes.
Do you know when the center value will it cause to turns into the sliding into the static
Nice,
friction?
So please come back to summarize.
We have discussed about the energy transformation, which will cause the energy loss. And we will be sure the kinetic energy it causes the acceleration and it causes the moment inertia to be different when the radius of the system is not the same. And we have discussed about the counter friction, is it rolling or sliding? And the opponent thinks that the sliding motion is caused by when is the elongation of the elastic band. In the pendulum behavior, we have discussed about the periodicity of the motion. It will be affected by the mass of the ball, and it will be affected by the elastic band because the moment inertia will increase while the mass increases. And this is about the elastic band elongation. The reporter says the sliding caused by the elastic elongation, and with the number.
So question from the viewer. You have 3 minutes.
Thank you for the report and your warning, and I have several questions here. So after as a report and your warning, how often do you change it as
You change it like for every 5 experiments.
I think because like the reporters have mentioned, it will cause the every time you need to change your elastic band to avoid the fatigue. Because the reporter said it will fatigue, the elastic band will fatigue. So the opponent thinks that the reporter should change the elastic band every time.
Okay, thank you. And how do you think the surface friction will affect the motion?
The subscription. Do you mean by the rate of one of the slide friction or the
Like if we don't stop the train, then what else? Have you tried like other sources?
other sources? Yes,
Yeah.
sure.
Okay, thank you.
I'm not an opponent.
Oh, sorry. Sorry, it's my. Okay, so about the topic that you just talked about, and I have an extended question. So like, you talked about like different size of the balls, right? So like I've observed that the elastic band when you climb in an outward, and do both of you think it will affect the
Can you say that again? Sorry.
like the two balls are different sizes, right?
Yes.
So the elastic band it climbs in an outward.
Yeah.
Yeah. So do you think it will affect?
Yes, I think things will affect. And I actually don't agree with the motion that you talked about, since when it's twisting, actually the ball on two sides should be twisting on the opposite direction. If it's on the same direction, then there won't be the ball then the twisting will not untwist. It will just stay at the same motion. Or others. Yeah, that's what I think.
I agree with that report.
Okay, so I've observed in this development that do you both like investigating or I think about the motion of the spinning rings? Like does the central part of the motion has a pattern? Like does it keep on the constant?
I think it will change the friction of two balls is different or the mass is different.
So will it rotate in the pattern or like it's spinning?
I think it will rotate in a pattern.
I think if you keep the surface, the contact friction is totally the same, it will not cause phenomenon like this.
Then how would you find your like, energy in setup?
Kinetic energy we define it by the tangential speed of the balls.
Okay, then.
Same as the report.
Okay. I think that's it.
You have 2 minutes.
Okay, so I will start start my review presentation about balls on an elastic band. We're going to Tim Tesla from the University of High School. Okay, so here's the problem statement, and that's about the connected metals with bars on the elastic band, and twist the elastic band and put the balls on the table. And also we're going to spin in one direction and not in the other. So we're going to explain the phenomenon and investigate how the behavior of such a pendulum depends on the relevant parameters. Okay, so I think here's my comments about the principles of the order and throws are the metal model and use many functions to improve, especially the energy part. I have good understanding of theories and thought about how to balance human heat. And the cons are the fail to accurately explain the use of functions and dimension. And the pros are of the opponent are the astonishing questions and the good opponent problems with the order and have good understanding of the report. And the cons are too much about rotating part instead of spinning part, and they do not ask that many questions about the shear of FK and lack of investigation on the fault itself. And so here's about the discussion topics. So the opponent asks for the spinning, where was frequency change and word unclear answer. And our opinions are we agree with the opponent and how to change. Okay, so and the other question of the opponent's initial conditions are important for experiments. And reporter initial conditions for the fact what I mentioned and we agree with the opponents. Okay, so here I believe are the points missed. So how would a surface friction affect the phenomenon? And how and what will happen if the ball oxidizes? And how will the length and the thickness of the band affect the phenomenon? And thus motion spinning and the placement of the central part as a pattern. And I believe that I agree with good discussion with both the reporter and the opponent. I would think both of them for good discussion. We'll go to see the end of our review. Thank you.
So, reporter is your 4 minutes.
Why don't we just go through comments and now I'll be starting my concluding remarks. Let's first talk about my improvements that we've done. First, about the experiments, we can more investigating about whether it's going pure rolling or there's sliding and rolling at the same time. And we can more discuss about the different sizes, different masses, and the elastic band. And about the error, we think that it may be caused by the uneveness of the surface, the temperature, the rubber band that touches the ground, and the fatigue that's caused throughout the system. And the rolling resistance, we think that rolling resistance still can be ignored, and the radial sliding may cause energy loss. And greater friction leads to long period and cause total cycles. How will be influenced by the status of the rubber band. And as I just mentioned, we think that different masses and different sizes of the ball might lead to different motion, and we can investigate more on different parameters between the two balls and not just the two have the exact same conditions. And thanks to the reviewer and the opponent, we think we have a great discussion and we'll learn a lot more from this theory. Thank you.
Okay. So, any questions from the jury?
Okay, so since we're looking at a radial direction, which when we see it, there will be two balls inside of one direction. And we think that the first thing that's affecting it is the damping from the rubber band. And yes, the damping.
No, I mean, what's the force to drive the
ball?
Yeah, that's the steady.
I believe it's fork, which is the kappa, where it's giving it.
So what's the force?
Okay, so answer. Okay.
It's the twisting force.
Twisting, yeah, okay. How about opponent?
But the opponent thinks that it is caused by the friction between the balls and the table.
Friction, okay, and the review.
I think it's a friction and also the tension and also the spring.
Okay, so thank you. So for the friction, for example, if you think that's the portion think that's the degree of rotational of the ball, okay? And then the motion is the two balls on the go around with the center of mass.
Yes.
So I think the degree, the angle is totally different from the twisting angle and the rotation angle? What's the difference between these?
I believe the rotational angle is when we're looking from the above,
Yeah.
and then spins on it, so it's just the tangential, it's related to the
Yeah,
tangential.
but the twist angle is not the.
Yeah, it's different.
Yeah, that's different. So how come your equation only one theta? I think that will be two angles.
Because I believe I can use this to explain time period.
Okay, how about component?
Can you rephrase your question?
Yeah, I think there are two angles, the twist angle and the rotation angle.
Yes, yes.
Why they not there only one theta in the equation? Yeah, how do you obtain?
Oh, the opponent thinks that if there is the rotational motion, you need to consider this angle too, and this will cause the with the moment as well. Yeah.
Okay, how about you?
So I think like both forces can like should be considered, and I think you should consider it like for any experiments.
So you think that should be two parameters, or only one parameter is okay.
I think that's
Two parameters.
I think there should be three because the elastic band will stretch.
Anyone has any comment? Okay, show the data about your velocity measurement because you also mentioned some noise from the three different regions, right? Can you show your plot? Because they look like the spike, and look like the noise. This kind of thing. Okay, start here. Yeah, the spike. That looks like the spike. You see that this one is the noise, right? Okay. So how about the corner of the zero? Do you agree is the reasons for the temperature and touch point, right? And the third one, do you also agree this one? You think this one is from the noise, from these reasons?
Noise.
Yeah, you say the noise, right?
The sound, the noise.
No, how do you say it? The noise.
The other factor that's going to
Yeah, I think the noise. The signal noise.
like the bouncing the ball or the orbit.
Yeah, do you agree?
I think this is caused by the trigger. When you capture each point, the frame of the picture is not equally the same.
So you don't agree, right?
Yeah.
How about you?
I don't actually agree. I
Any question? No? Okay, thank you. So we need a jurors to prepare your score. So when ready, let me know. So, you show the score for the reporter. 8, 7, 7, 9, 8. Okay. So the next one is opponent. Show the score. 8, 8, 7, 8, 7. Thank you.
Thank you.
The final one, ruler. Okay, show you score. 8, 7, 7, 8, 7. Okay, thank you. So we come back in 10 minutes.